After completing this section, you should be able to achieve the objectives shown on this slide. By demonstrating competence in Rstp, you should be able to identify the enhancements made to STP to achieve faster network convergence. Rstp IEEE 802.1w is an improved version of STP IEEE 802.1d that addresses the long convergence times of its predecessor. Rstp uses the same STP criteria for route bridge election and best route path selection. Although Rstp introduces new port roles and states, the way the protocol determines the port roles and states is similar to STP. Like STP, Rstp relies on BPDUs to operate. BPDUs are sent at the interval defined by the hello timer, 2 seconds by default. The Rstp BPDU format is the same as in STP except that Rstp includes protocol-specific information in previously unused bits in the BPDU flags field. In addition, the protocol version in the BPDU is set to 2 to indicate Rstp, instead of 0, which indicates STP. The most important benefit of Rstp is its much faster convergence to topology changes. With STP, the network takes between 30 and 50 seconds to converge, whereas in Rstp, it can take 6 seconds or less. Rstp provides faster convergence because it does not use the forward delay and max age timers used by STP when responding to network changes. Instead, the switch quickly exchanges BPDUs with the adjacent Rstp switch to determine the new port roles. In other cases, the switch just moves a blocking port to the forwarding state immediately after it detects the network change. Rstp is backward compatible with STP. When an Rstp switch receives an STP BPDU on a port, the switch begins to use the 802.1d rules on that port. Conversely, if the switch receives Rstp BPDUs, the port operates according to the 802.1w rules. Rstp simplifies port states by combining the states that drop user traffic, disabled, blocking, and listening, into a new state called discarding. The other two states, learning and forwarding, behave the same as they do in STP. Rstp also introduces two new port roles that better define the role of the STP blocking port, alternate and backup. The other two port roles, route and designated, work the same as in STP. An alternate port has a less desirable, higher cost path to the route bridge than the route port, and is also connected to a different switch than the route port. A backup port is a redundant, less desirable path to a segment where another, more desirable port is already connected. The example on this slide shows the port roles determined by Rstp for the same topology used in STP. The route ports and designated ports are determined by Rstp in the same way as by STP. However, for the backup ports, Rstp classifies them into alternate ports or backup ports. The roles of the alternate ports and the backup ports in the topology are determined as follows. Switch 2, port 2, the port is connected to the same switch, same path to route, as port 1. Therefore, port 2 is a backup port. Switch 3, port 2 and port 3, the ports are connected to different switches from the one the route port is connected to, different paths to route. Therefore, both ports are alternate ports. Switch 4, port 1, like port 2 on switch 2, this is a backup port. When a port comes up or down in a network, STP must determine if there are changes in the port roles for the new topology. The ports which roles change from blocking to designated or route go through the listening and learning states before being placed in the forwarding state. This means that the network does not converge before around 30 seconds have passed. In contrast, Rstp provides much faster convergence because it does not rely on the STP timers to determine the port roles. Instead, it considers the following variables on a port. Edge port. This is a port that connects to a single endpoint. Because such a connection won't result in a loop, Rstp places edge ports in the forwarding state immediately after the port comes up. Edge ports send BPDUs and listen for incoming BPDUs. If an edge port ever receives BPDUs, the port loses its edge status and becomes a regular STP port. Note that you must manually configure the port as an edge port. Alternate and backup ports. Right after the root port on a switch fails, Rstp moves the alternate or backup port with the next best root path to the forwarding state, and then sets it as the new root port. Link type. Non-edge ports that operate at full duplex are considered point-to-point links and therefore candidates for fast transition to the forwarding state when the topology changes. For this, Rstp exchanges a proposal agreement handshake to decide the state of each end of the link. Non-edge half-duplex ports, however, are considered connected to a shared medium, like a hub, where multiple switches may be also connected. Rstp then uses the traditional and slower STP convergence process on half-duplex ports. In the example shown on this slide, the switch ports that connect to the PCs are configured as edge ports. In addition, all switch ports, except those connected to the hub, operate at full duplex. Consequently, on ports other than port 3 on switch 3 and port 3 on switch 4, Rstp can provide rapid transition to the forwarding state. Rstp provides faster convergence than STP when you add a link to a switch in your network. Before describing Rstp behavior, let's first explain how STP reacts to such a topology change and the time it takes for the protocol to converge. 1. The network is stable, and the roles of the ports have been determined from the root bridge, switch 1, perspective. The PCs can communicate with each other through the link between switch 2 and switch 3. 2. A new link that connects port 2 on switch 1 and port 2 on switch 2 is added. The two ports will be placed in the listening state to check for incoming BPDUs. If the BPDUs are superior, the switches relay the BPDUs to their neighbors. 3. Switch 2 receives a superior BPDU, lower root path cost, on port 2, and assigns the port as its new root port. Switch 2 also relays the superior BPDU to switch 3. Switch 3 receives the BPDU from switch 2, but does not consider it a better BPDU than the one received on port 1, and therefore, does not relay it. 4. The link between switch 2 and switch 3 is now an alternate path to the root bridge, and for this reason, it is blocked by STP. Both switches have the same root path cost, but switch 2 has a lower bridge ID, and therefore, port 1 on switch 2 becomes the designated port, and port 2 on switch 3 becomes the blocked port. The previous steps take place very quickly. That is, STP determines a new root path for switch 2, and blocks the alternate path very quickly. However, port 2 on switch 1 and port 2 on switch 2 still need to complete the transition through the listening and learning states before they start to forward traffic. This means that the PCs won't be able to communicate using the new path, through switch 1, for the next 30 seconds or so, a waiting time that is considered unacceptable by today's availability standards. Now, you will learn about how Rstp reacts to the same topology change. 1. The network is stable, and the roles of the ports have been determined from the root bridge, switch 1, perspective. The PCs can communicate with each other through the link between switch 2 and switch 3. 2. A new link that connects port 2 on switch 1 and port 2 on switch 2 is added. The two ports are placed in the discarding state to check for incoming BPDUs. 3. Switch 1 sends a BPDU proposal to switch 2 to let switch 2 know that it has a superior BPDU. Switch 1 is the root bridge. 4. Switch 2 realizes that switch 1 has a superior BPDU and therefore, that it must assign port 2 as its new root port. But before doing that, switch 2 places all its non-edge ports to the discarding state to ensure no loops are formed later, when the ports on the new link are moved to the forwarding state. The only non-edge port in switch 2 is port 1, and it's placed in the discarding state. This mechanism of placing non-edge ports in the discarding state, before the switch agrees to a superior BPDU proposal, is called synchronization. 5. Switch 2 sends a BPDU agreement to switch 1 to indicate that it accepts the superior BPDU. Both switches then place their respective ports in the forwarding state and assign their roles. Note that there is no loop in the network because port 1 on switch 2 is in the discarding state. From this moment on, the PCs can reach each other using the new path formed by switch 2, switch 1, and switch 3. 6. Switch 2 sends a BPDU proposal on each non-edge port that is currently in the discarding state, which in this example is only port 1. 7. Switch 3 ignores the BPDU proposal from switch 2 because it is receiving superior BPDUs from switch 1 on port 1. Instead of sending a BPDU agreement to switch 2, switch 3 sends its own superior BPDU to switch 2. 8. Switch 2 and switch 3 realize that the link between them is an alternate path to the root bridge and therefore must be blocked to prevent a loop. Both switches have the same root path cost, but switch 2 has a lower bridge ID, and therefore, port 1 on switch 2 becomes the designated port, and port 2 on switch 3 becomes the alternate port. Like in STP, the previous steps also occur very quickly, and the resulting loop-free topology is also the same. However, unlike STP, Rstp does not use timers for transitioning the ports to the forwarding state. Instead, when the topology changes, Rstp uses a proposal agreement handshake and synchronization mechanism between adjacent switches to quickly determine port states and roles, while also ensuring that the network stays loop-free. This process repeats itself on links connecting non-edge ports that were put into the discarding state during synchronization, and ends when adjacent switches ignore the sender's BPDU proposal, and Rstp blocks the alternate path. Good job! You now understand Rstp. Now, you will learn about Multiple Spanning Tree Protocol, MSTP.